Remember this slide? Remember this reaction? We said it's a new type of reaction. It's called a substitution reaction. All of those other alkene and alkyne reactions were addition reactions. Well, this one is a substitution. It's time to learn all about substitutions and eliminations. So there are three major classes of organic reactions: additions, substitutions, and eliminations. In a substitution reaction, one group replaces another. We've got this thing and this thing reacting together. Who is electron rich? Who has a pair ready to share? This guy. He's our nucleophile. This thing has a partially positive carbon. Why is that carbon partially positive? Because there's a dipole headed toward the bromine. So that partially positive carbon, that's our electrophile. The carbon is our electrophile. In all of these chapters, in this chapter on substitution and elimination, that group that is the electrophile is called the substrate. The substrate and nucleophile react together to make these products. We said one group replaces another. This thing went away and this thing took its place. One group replaces another. Substitution. We have our product over on the right-hand side. That's our alcohol in this specific example. And that Br, that left, is known as our leaving group. So Chapter 9 is all about substitutions and eliminations. We're going to use alkyl halide substrates in all of Chapter 9, alkyl halides as substrates, but we will use a ton of different nucleophiles to make a ton of different types of products. But every time the substrate is going to be an alkyl halide. Yeah. That's substitution. What about elimination? In elimination, a hydrogen and a leaving group are eliminated. In all of this chapter, who's the leaving group? A halogen. So a hydrogen and a halogen are going to go away, and you're going to get a brand new pi bond. In this bottom one, this guy, he has a pair ready to share. Instead of calling him a nucleophile, we're going to call it a base. Give me 1 second to explain why. Hold on. But we're going to lose hydrogen and a bromine and have a pi bond made. So we lost the hydrogen from this top carbon to make that CH2, a new pi bond. We lost water in the process and a Br minus. That was our leaving group. Okay. We will talk at length about substitutions and eliminations. But if I drew all of those H's out explicitly, this hydroxide is going to react with an H and kick out my Br that way. We're going to talk at length about the mechanism involved, but the reason this hydroxide is often called a base down here is because it's meant as a Bronsted base, because it's reacting with a hydrogen in a Bronsted base way. This is reacting as a Lewis base. It's donating a pair, so the Lewis base cleaner term is to call it a nucleophile. So they're both an alkyl halide substrate reacting with hydroxide, but we call the thing that it's reacting with slightly different things, whether it's a substitution or elimination, because whether you're reacting with a hydrogen or a carbon, you call it a substrate, a base or nucleophile. Maybe that made sense. So we're going to start out talking about substitutions at length. Lots and lots and lots of substitutions. There are two main types of substitution reactions. First of all, substitution always competes with elimination, and what makes this unit of material a little bit tough is we spend a long time establishing what Sn2 is, what Sn1 is, and a little preview, what E1 is and what E2 is. Maybe you can deduce what some of those names stand for. We spend a long time talking about what those four reaction types are, and then we finally say, but really, it's all in competition, and you have to know the conditions very well to know, under these conditions, I should get that product. Under those conditions, I think I should get this product. Okay, enough of a preview. There are two main mechanisms in Chapter 9, two main substitution mechanisms, Sn2 and Sn1. We've actually already seen Sn2 one time when we did acetylide reactions. Sn2 stands for substitution, nucleophilic, bimolecular. Okay. That reaction is a one-step concerted reaction. Sn1 stands for substitution, nucleophilic unimolecular. Okay, cool. So what? It goes through a super familiar intermediate. Whew, I feel comfortable with these. It goes through carbocations. Yep. So all that stuff that you learned about carbocations previously, they can shift here, they can shift there. It's all still relevant because Sn1 stuff is going to make carbocations. The mechanism is super important this time. Like I said, we've got a lot of competition happening between all these 4 different mechanism types, and we have to use our context clues to figure out which mechanism it should be. First of all, should it be substitution or elimination? Second of all, should it be Sn1, Sn2 if it's substitution? So it matters a lot. The mechanisms are different, and the types of products you get are often different. We're going to talk first in great detail about Sn2. This is an Sn2 reaction. Are you ready? So we've already established hydroxide is our nucleophile here. He's got a pair. He's ready to share. And the carbon of my alkyl halide is partially positive because there's a dipole pointed that direction. So hydroxide attacks the carbon of the alkyl halide and pops off the bromine. It's a concerted mechanism, so you get the product immediately in one step, ta-da, like this. And bromide left as a bromide that's negatively charged. Yeah? We made those 2 products. But you've seen enough organic now to know we often don't even draw this little side product, but I'm drawing it there because this is our first time talking about Sn2 as an alkyl halide thing, except with acetylids, but yeah. Somewhat frequently, when a reaction is concerted, we draw a reaction, a transition state of that reaction. What does it look like when the bonds are being made and the bonds are being broken? So I've got hydroxide coming in from one side, trying to make a bond to this carbon, and I've got bromine trying to eject on the other side, like that. This carbon up here is sp3 and trigonal, sp3 and tetrahedral, 109.5 bond angle, and so is that one. But what happened was, when hydroxide attacks, he's got to attack from the backside because that bromine is taking up all the real estate on the front side. So hydroxide does a little backside attack, busts out the bromine like that, and look, it's like my umbrella got inverted on a windy day. My hydrogens were all pointed left up here, and now they're all pointed right. I actually did that on purpose, believe it or not. It goes through this sort of planar-looking structure in the transition state where all of the hydrogens are kind of trigonal planar all in one plane here. That carbon in the middle, partially positive, bromine's partially negative, hydroxide partially negative. You're making a new carbon-oxygen bond, breaking an old carbon-bromine bond. A transition state shows what's being made and what's being broken, all the little dot, dot, dot bonds. So this is a concerted mechanism, but we often show a little transition state as part of our concerted bit, especially for an Sn2. Okay? This says, let's write the rate law. What? That's old GChem stuff? Yeah. Rate law stuff. This Sn2, 2 stands for bimolecular. What that really means is that 2 things are colliding in the rate determining step. So this rate law looks like this. Rate equals K times, remember old GChem knowledge, rate equals K times the concentration of reactants. Are both reactants involved in the rate determining step here? Yes. Because it's bimolecular, both reactants are involved in this rate determining step, so that's what my rate law looks like for this specific reaction. But an Sn2 reaction in general is a nucleophile times a substrate. S-T-R-A-T-E. Ugh, blah. I do know how to spell. I won a spelling bee when I was in 2nd grade. Yeah. So the second order overall, that's because it's first order in hydroxide, first order in substrate, second order overall, bimolecular, second order overall. That's what all that stuff means. That's breaking down the jargon. The stereochemistry that's observed. Well, we have previously said that all concerted reactions show syn stereochemistry. We should adjust that definition a little bit. All concerted addition reactions show syn stereochemistry, but this is not addition, this is a substitution. This substitution happens backside attack, whoosh, whoosh, like that. So what actually happens to this carbon is inversion of configuration. Is this, can't write and talk at the same time, is this carbon an asymmetric carbon? No. Does it matter that these hydrogens were pointed left and now they're pointed right? No. There really is no net difference in this specific example, but in Sn2 in general, you should get inversion of configuration. So for various substrates, that looks a little different depending on what you were given in the beginning. Got it? All right. Let's draw a little reaction coordinate. How about it? We're going to draw energy on the y-axis, reaction progress along the x-axis. We're going to put our little substrate. That's a methyl over here on this little end. That's a CH3. Yeah, CH3Br. We're going to put a little shelf down below because assuming this reaction is exergonic, assuming that products are more stable than reactants, we're connected with one Lumpty Humpty bump because there's only one step. It's a concerted reaction. There's a transition state up front and up top, and if I asked you, what does that transition state look like? You could draw it for me, couldn't you? Yeah, I think you could. We just did. The activation energy for the reaction is from the reactant's shelf to the top of the highest hill. That's the EA of this reaction, EA Sports. My delta G, if this is a G plot, or my delta H, if this is an H plot, that's the products minus the reactants, the difference in energy in those two shelves. Yeah? Sn2 has a pretty nice little reaction coordinate because there aren't any intermediates formed in this Sn2, in any Sn2. Okay, cool. So up next it says different substrates. That's a super helpful title right there. What substrates are we doing in all of this chapter? Alkyl halides. So why do we need a whole slide that says different substrates if they're all alkyl halides? Well, those alkyl halides could be a lot of different variety, such as CH3, halogen, CH3CH2, halogen, CH3CH, CH3, halogen. Yep, no need for me to try to continue with all the C's and H's stuff. Yeah. This top one is a methyl alkyl halide. We're going to call it AH because it takes me too long to write alkyl halide when I'm trying to talk at the same time. A methyl alkyl halide. The second one is a primary alkyl halide. Third one, secondary alkyl halide. And the last one, tertiary alkyl halide. How do I know what's primary, secondary, tertiary? Methyl means plain methane, one hydrogen has been removed and replaced with a halogen. Primary alkyl halide means the carbon that the halogen is connected to has how many other carbons connected. It has one other carbon connected, it's primary. The carbon that the halogen is connected to has two other carbons connected, it's secondary. The carbon that has the halogen connected is tertiary. Yeah, okay. So what's so good, bad, ugly about these things? Is a methyl alkyl halide a good substrate for Sn2? Yeah, it's an excellent substrate for Sn2. It's a really fast reaction. Primary is real good. We might even say it's a great substrate for Sn2. Secondary, it's bordering on okay. It's bordering on good. It's not the happiest to do Sn2, but it can. Tertiary, it ain't happening. Tertiary cannot do an Sn2 reaction. Tertiary, Sn2, not a thing. Don't do it. Tertiary, not a thing. So based on this, it seems the trend is less crowded substrate equals better. So for alkyl halides that are methyl, Sn2 is real fast. Primary, also good. Secondary, doable. You're getting more crowded as you get more substituents around, and that's not great. Why not? Because where is that nucleophile attacking from? It's got to do a little backside attack. And a tertiary is so crowded on the backside that that nucleophile cannot get to where it needs to go. It's too crowded. This little carbon, too crowded. That nucleophile cannot do a backside attack. So we want less crowded substrates because they're better. They're faster. So methyl is the fastest. Primary is next. Secondary is the slowest with Sn2. Okay, hold that thought. Aren't there other kinds of substrates that could do Sn2? Yeah. There's benzylic and allylic. And there's aryl and vinyl. Two of these are kind of okay / could be really good. Two of these are really not so good. Aryl and vinyl, nah, don't do it. Those are bad substrates for Sn2. Benzylic and allylic, they're great if, that's a big if, not tertiary. So you could have something primary and benzylic, it's really fast at doing Sn2. Something that's tertiary and benzylic, you can wait all day long, 300 years, maybe not quite that long, and it would not do Sn2. Yeah? Okay. Crowding is a big deal. Tertiary, not going to happen. Got it? Okay. Branching at the beta position also inhibits reaction. That sounds real fancy, doesn't it? Branching at the beta position, yeah, this is where my halogen is. That's called the alpha carbon. That's called the alpha carbon. Next door to the alpha is the beta. Here's the alpha. Clicky, clicky, come on. Here's the alpha, there's the beta. So if you compare the betas of the top example, there are 3 hydrogens. The beta of the middle example has a carbon and 2 hydrogens. The beta of the bottom example has 3 carbons. Carbon is physically a bigger atom, but additionally, the carbons always have hydrogens connected to them. So this beta in the bottom has so much hindrance to the alpha carbon next door that it greatly slows down the reaction. My laser's not showing up. Oh, the struggles. So if we rank these in order of speed, they are all primary alkyl halides. But when there gets to be a lot of junk at the beta position, it also slows down your reaction. All right. This says Sn2 is related to acid-base reactions. What does that mean? This is hopefully a familiar acid-base reaction. Hydroxide plus HBr. This is my acid. Creates water and Br minus. This is my conjugate acid. If I list the pKa of my acid and the pKa of my conjugate acid, remember equilibrium always favors the weaker acid-base pair. So we favor the products up here. What does that have to do with a substitution reaction? If you talk about or consider your nucleophile here as a base, and your nucleophile and your leaving group here as a base, equilibrium always favors the weaker acid-base pair. So just like up here, I could say this base versus that base. This base is much weaker. That's how I know that equilibrium favors that side. I know that base is weaker because I know that acid is stronger. This acid is stronger. Okay. So hydroxide, conjugate acid water versus Br minus, conjugate acid HBr. HBr is a strong acid, therefore Br minus super weak base. Equilibrium favors the products side. What that translates to in a substitution reaction is weak bases are good leaving groups. Strong bases are terrible, horrible, no good, very bad leaving groups. Strong bases are terrible leaving groups. So we said this time all of our substrates are going to be alkyl halides. And now I hope you can understand that the reason for that is because halogens are super weak bases, therefore they're excellent leaving groups. Are some halogens better leaving groups than others? Yeah. This is an I. This is a Br. Reacting with the same nucleophile, I minus versus Br minus. Oh, laser, laser. I minus versus Br minus. The weaker base is I minus because HI is a stronger acid than HBr. Because HI has I, which has a big radius, atomic size, bigger radius, bigger, stronger acid. Whew, yeah. F minus is not a good leaving group. It's the strongest of the halogens. It's the strongest base of the halogens. It's the worst leaving group of the halogens. So we'll actually see Cl minus, Br minus, and I minus leave, and you gotta know who's the better leaver of those. Chapter 10 is all about the same reactions, Sn1, Sn2, E1, and E2, but with different leaving groups, as in alcohols, different substrates, alcohols, ethers, epoxides, sulfonium salts, amines, amides, ammonium salts, all kinds of things. That's chapter 10. Not now. We're in chapter 9. All right, so we're doing substitutions with substrates that are all alkyl halides, but we said our nucleophile is going to be different in lots of our reactions. Here are a few examples of excellent nucleophiles and a few examples of good nucleophiles. You should write these down. You should include the brackets that are around these. Well, let me explain why the brackets are there. In order to be a good nucleophile, you need to be capable of sharing electrons. All of these things are capable of donating and sharing electrons. These things in brackets are capable of sharing, donating to a carbon, but they're also very good at plucking hydrogens, as in the 4 that are in the brackets are also considered strong bases. Everything else that's outside the brackets under excellent and good, those are not strong bases. Those are nucleophiles. They can be considered bases because all nucleophiles can be considered bases, but they're considered strong bases in the brackets. Okay, why might some of these be excellent and why might some of these be good? Well, if you notice, a lot of these that are excellent have negative charges. Some of them that are good also have negative charges. Okay. Take this first one, for example. This is the carboxylate, the conjugate base of a carboxylic acid. It's got delocalized electrons, and when you have delocalized electrons, is it easy to give a pair of electrons away when you can't really find your pair? It's kind of spread all over the place? No. So things that have delocalized electrons are always weaker nucleophiles and weaker bases than things that have localized electrons. We've actually said that before. Put a sulfur with a minus up here, sulfur with no charge down here. Yeah, sulfur, good nucleophile. It's a very large radius atom. Large radius atoms are often good nucleophiles. They're very polarizable. Yeah, it's a thing you should have talked about in Gen Chem. Polarizable atoms, good nucleophiles. Okay, that's enough about that. I said that was all, but I changed my mind and have 2 more things to say. Remember, nucleophile strength is about attacking strength, how well this atom can attack the positive carbon, partially positive carbon. Because Sn2 reactions involve the nucleophile in the rate determining step in the rate law, if you have a high concentration of nucleophile, it makes the reaction go faster. But also, if you have a stronger, better nucleophile, it makes the reaction go faster. Okay, that's really all. Nucleophiles versus basicity, nucleophilicity versus basicity. Usually, base strength parallels nucleophile strength. What that means is if something is a better base, it's a better nucleophile. If something is a better base, it's a better nucleophile. Usually. Why not always? Well, if you have a protic solvent, we're going to talk about solvents momentarily. If you have a protic solvent and you're trying to do a reaction, if you have 2 different atoms that could be nucleophiles, and those 2 atoms are in the same group, meaning periodic table group, the bigger the atom, the better the nucleophile. Bigger atom, better nucleophile. This is a rare occasion to have a bigger atom, better nucleophile. In general, the smaller atom is the stronger base, which means that the smaller atom is the better nucleophile. So why is it different in this context? Give me a moment. If I compare things like NH2 to OH minus to F minus, the deal with those three examples is they are next door neighbors on the periodic table. So remember, when we talked about acid and base trends, these guys, it was not about radius, it was about electronegativity. So we're really saying, let's compare this acid to that acid. If we're comparing those three acids, the strongest acid on that list is HF, then next is H2O, then last is NH3. HF is the strongest acid because all of those atoms, N, O, and F, are similar radiuses, similar radii, and F is most electronegative. So HF is the strongest acid, which means F minus is the weakest base. And we said base strength usually parallels nucleophile strength. So NH2 minus is the strongest base. It is also the strongest nucleophile, regardless of solvent. The only time that things are different is when you have a protic solvent, you have nucleophilic atoms that are different, but in the same group. So we're going to flip to a new slide, but that's things like Cl minus, Br minus, I minus. Yeah? So let's compare Cl minus, Br minus, I minus. Why do I write these in a column? Because that's how they are on the periodic table. They are upstairs, downstairs neighbors. We're really saying HCl versus HBr versus HI. Which acid is the strongest? This is the strongest acid. Therefore, that is the weakest base. So if you are in aprotic solvents, I always have to pause to say the right thing. If you're in aprotic solvents, better base, better nucleophile, just like we discussed. So in aprotic, Cl minus is the best nucleophile, and I minus is the worst, and Br minus is in the middle. In protic solvents, the trend is reversed. In protic solvents, I minus is the best, and Cl minus is the worst, and Br is in the middle regardless. Why is that the case? Well, I stole a figure from your textbook. This is it. It says small atoms have very strong ion dipole interactions between your polar protic solvent. Methanol is a polar protic solvent. Small radius atoms have a very strong ion dipole interaction. Big radius atoms have a very weak ion dipole interaction. So in order for a nucleophile to attack something, attack, you're going to need to break some of these, or at least one of these, ion dipole interactions. And it's easier to break a weak ion dipole interaction than it is to break a strong ion dipole interaction. So the bigger atom has fewer solvent molecules or weaker solvent molecule interactions. So you break off a solvent molecule interaction and you attack the electrophile that you were trying to attack. Anyway, this is a pretty strong bond, and that's not so easy to break. So students sometimes get really hung up on this, and they spend a long time studying this and worrying about this, but there are 4 possible cases. If your solvent is aprotic, you don't care. Better base, better nucleophile. The 4 cases that I mean are your 2 different nucleophile atoms are in the same period. We don't care. Better base, better nucleophile. the two nucleophile atoms are in the same group, we don't care. Better base, better nucleophile. In aprotic solvents, better base, better nucleophile. In protic solvents, if your atoms are in the same period, better base, better nucleophile. 3 cases, better base, better nucleophile. If your solvent is protic and your atoms are in the same group, bigger atom, better nucleophile. It's real complicated to explain, but it's not super complicated to understand, I don't think. There's not a ton of options. There's not a ton of examples that we will work through like this because it's not the case most of the time. The textbook makes a bit of a bigger deal about solvents than we will. Better base, better nucleophile will get us through most of the stuff that we need to do. All right, I'm ready to move on. You ready? So we just preached for a while about solvents, protic solvents and aprotic solvents. What the heck are protic solvents and aprotic solvents? Protic solvents have hydrogen bonding. Aprotic solvents don't. What does it mean to have hydrogen bonding? Hydrogen directly connected to nitrogen, oxygen, or fluorine. So protic solvent examples. This is not an exhaustive list, but protic solvent examples. Water, methanol, ethanol, isopropanol. All of those are what functional group besides water? Alcohols, yeah. Acetic acid is a common protic solvent because it's a liquid and it has hydrogen bonding, yeah. Yeah, that's a lot of them. There are maybe a few more. Aprotic solvents. We're going to say they're often written as acronyms. Yep, acronyms. Often written as acronyms. So we've seen some aprotic solvents. This is not an acronym, but we saw CCl4 before. CH2Cl2, okay. We've seen THF in our previous reactions. That's tetrahydrofuran, that's him. Diethyl ether is an aprotic solvent. DMF, that's NN-dimethylformamide. That's this crazy thing. NN-dimethylformamide, DMF. DMSO, dimethyl sulfoxide. Acronym, THF, DMF, DMSO. Acetone is an aprotic solvent. Hexane is an aprotic solvent. What's different about hexane and carbon tetrachloride, that's that first one, those two are both nonpolar aprotic solvents. Generally, in all of this stuff we're doing now, we will see polar aprotic solvents, but those two are nonpolar. Okay. Can I think of any more? Not right off the bat, but that's not an exhaustive list. There are lots of examples of them. You'll probably come across a lot more that I'll say, I should have mentioned that one too, but that's all I've got right now. I think we've said most of the things we need to say about Sn2. We said methyl is fastest, primary is real fast, secondary can happen, tertiary not so much. Allylic and benzylic are fast, as long as not tertiary. Remember that? Yeah, we said that. Aryl and vinyl, Aryl and vinyl, it ain't happening. Leaving groups. Weaker bases make better leaving groups. That is always and forever a true statement. It's not just an Sn2 reaction statement. That is always and forever a true statement. Weaker bases make better leaving groups. Period. High concentration of strong nucleophiles makes the rate faster. Because nucleophiles concentration is involved in the rate law, is involved in the rate determining step. Okay, we did not say this, but in general, an aprotic solvent is a reaction in an aprotic solvent is a faster reaction than the same reaction in a protic solvent. That was too many words to explain a simple greater than, less than. An Sn2 reaction in an aprotic solvent is generally faster than the same reaction in a protic solvent. Okay. The reaction is concerted. It's a single step, concerted, which means you do not have any chance for rearrangements because you don't make a carbocation. The stereochemistry is inversion. You ready to talk examples? I'm ready. You ready? All right. Since we said Sn1, Sn2, and E1 and E2 are always in competition. I want to get you used to looking at a problem and saying, which one is my substrate? This is my substrate. That substrate is an alkyl halide. That substrate is a secondary alkyl halide. So I want you to categorize that's a secondary alkyl halide substrate. Okay. Then I want you to look here and say, that nucleophile, is that an anionic nucleophile or is that a neutral nucleophile? Because this is CH3, S, Na, sodium don't really make bonds, that's an ionic thing. So that means sulfur is my actual nucleophile, and it's an anionic one. So secondary alkyl halide substrate reacting with an anionic nucleophile. The only reaction I know how to do so far is Sn2, but the evidence we're going to gather is secondary alkyl halide, anionic nucleophile, Sn2. Let's do that reaction. The way that goes is nucleophile attacks the carbon that has the halogen connected. Bromide pops off. There's my product. That product did not, or that reactant, did not have any stereochemistry, so there's no reason to include any stereochemistry in my product. But what if my reactant did have stereochemistry? It's the very same secondary alkyl halide, the very same ionic, anionic nucleophile. Sulfur attacks the carbon that has the halogen connected, pops off the Br, and my product is drawn that way. Why is my product drawn that way? Because inversion of configuration. When I kept my backbone that's in the plane, all my stuff that's in the plane stayed exactly the same. Everything stayed the same. Backside attack means the nucleophile is going to come in with a dash if the leaving group had a wedge. That's if I kept my backbone in the same orientation. I could also draw my product this way down here, where my methyl pointed down stayed in the same orientation, but my propyl over here got flipped to the other side. Both of these show inversion. What I want to tell you to do is pause and assign R's and S's and convince yourself that these two molecules are the same. This is not saying that these should both be drawn. It's choose one way or the other and draw it that way and be satisfied. If we go through and assign absolute configuration, this top molecule is R. This bottom molecule is also R. So in this bottom example where I started with one enantiomer, a chirally pure compound, I also ended up with one enantiomer, a chirally pure compound. So if I ask the traditional question, would you expect the product as obtained in this reaction to be optically active, you would say 100% yes. This is optically active because it's a single enantiomer. It is not a racemic mixture. It is not a meso compound. It does have an asymmetric carbon that is explicitly defined. All right. What if I drew the reactant a different way? Fisher projections. It's the same dang thing that we just did. Sulfur attacks the carbon, kicks out the Br. I've chosen to draw the product this way, but could you draw it a different way and it still be the same product? Yeah, you could. You just need to make sure that it's R or S the way it's supposed to be in the end, that your stereochemistry has been inverted. One word of caution. With what I just said, I said check your R's and S's to make sure it's inverted. Note, my leaving group was priority number 1. My incoming nucleophile took over priority number 1. Anytime your outgoing and incoming are the same priority, it does actually mean R changes to S and vice versa. When your priorities shift, it's not necessarily R becomes S and vice versa. Be careful. Okay. Up next, beware of intramolecular reactions. Okay. So I'm adding NaH to this thing. This is a secondary alkyl halide substrate, an NaH, that's an Na plus and an H minus. Sodium hydride, Na plus, A minus, H minus. That's an anionic thing. But H minus, not usually an attacker if there's a hydrogen to react with. Wait, what? So sometimes atoms can be a nucleophile, and sometimes they could be a base. Sometimes, depending on the substrate, they could be either. Anytime it has the option to do something as a base and the option to do something as a nucleophile, the acid-base reaction happens faster than the nucleophile reaction. So acid-base kinetics, the speed of an acid-base reaction is much faster than the kinetics of a substitution or an elimination or an addition. So really, anytime something could be a base or could be a nucleophile, number one, he's got to be a base because those kinetics of that reaction are so fast that it can't be a nucleophile before it does its acid-base thing. So why did I go on that little rant? Well, because I have an H connected to an oxygen here. I'm just drawing that H out explicitly. That's a pretty acidic hydrogen, not like crazy acidic, but pretty acidic. Sodium hydride can definitely deprotonate an alcohol like that. So out of deprotonating that alcohol, I end up with this O minus and this Br. So after the acid-base reaction is done, I get this blue product. This blue product is not my final product. It does not sit around. We've been talking about Sn2. Did I do an Sn2? All I did was acid-base. So what comes next is this is my nucleophile, and this is my substrate. They're in the same molecule. The substrate, the nucleophile, the electrophile, all in the same molecule, intramolecular. Okay, so I do a little whoopsh. If you could see me with my hands and my arms, this thing attacks that thing, kicks out that thing. We end up with this thing. So many things over here. An intramolecular Sn2. So this purple bit is my actual Sn2 reaction. This is a two-step sequence, a two-step reaction, but only the purple bit is called Sn2. Sn2 is concerted and inversion. Remember, oxygen attacked from the backside, kicked out the bromine, the opposite side kicked out the bromine, so that's why the oxygen is wedged over here. It stayed connected over on that carbon the whole time, so he was wedged the whole time. You kicked out a bromide as your leaving group. What is the functional group down here? This is an epoxide. Do you know other ways to make epoxides? Heck yeah, you do. While we're at it, what's the name of this functional group here? This is a halohydrin. Do you know how to make a halohydrin from, let's say, an alkene? Heck yeah, you do. You add Br2 and water to an alkene to make a halohydrin. Yeah. Organic's pretty cumulative. All right, just a couple more examples together before I let you go on your merry way. I have, in this top example, an alkyl halide. It's a secondary alkyl halide. This NaS, that's really an ionic thing. That Na and S, they're not making a bond. Na is plus over here by himself, and that sulfur is negative by himself. That's an anionic nucleophile. Sulfur is minus. We didn't analyze this before, but DMSO is an aprotic solvent. The only reason the solvent really matters, we're going to talk about solvent a little bit more, but the only reason solvent really matters is if you're comparing reaction speeds. Something like this top reaction in DMSO compared to this top reaction in water, you need to be able to compare and contrast those two kinetics, those two reaction rates, and a little bit more. We'll talk a little bit more. Okay. Secondary alkyl halide, anionic nucleophile, aprotic solvent, just cause. Sn2. Let's do an Sn2 reaction here. Sulfur attacks the carbon that has the halogen, and busts out the Br at the same time. If I keep my backbone, my stuff in the plane, in the same orientation, and I stick my sulfur up, like this, that sulfur needs to be dashed in order to show inversion of configuration. Is that the only acceptable way to draw this product? No. All right. You can handle that pretty well. What if I threw in one more little confusing bit? What if this sulfur compound had a defined stereocenter in the beginning? Should that stereocenter be dashed, or should that stereocenter be wedged? That stereocenter should be wedged because the reaction did not happen at that asymmetric carbon. Did not happen up here, so that stays the same. It did happen down here, so that one undergoes inversion. Yeah, we cool? Cool. All right. Secondary alkyl halide. Anionic nucleophile. That O and Na are not connected. The Na is over there by himself. Anionic. An aprotic solvent. Sn2. That's the only reaction we've learned, so hopefully you already knew that's what you should do. Yeah. O-, the nucleophile attacks the carbon with the halogen, and you get this. But wait, there's more. The carbon that got attacked, that carbon should show inversion, and the way to show inversion is with a dash. The carbon over here that had a wedge that did not get attacked should be a wedge, because he did not get attacked. Stay the same. Ta-da! Isn't it lovely? Yeah. That was so fun. How about some more? I have this is a primary alkyl halide substrate. This must be my nucleophile because he's got a minus. It's an anionic nucleophile. It's an aprotic solvent. Let's do some Sn2. It's a little bit difficult to compare, but if I were comparing, it's a little bit difficult to compare, but if I were comparing this reaction and the last two, which one would you think might be faster? This one, because this one is a primary alkyl halide, and those previous two were secondary alkyl halides. It's a little bit difficult to compare because they're not quite similar enough examples, but nevertheless. Anionic alkyl halide, anionic nucleophile attacks the carbon that has the alkyl halide on it. Attacks the carbon that has the alkyl halide on it. And then we kick out the alkyl halide. If I keep everything in the same orientation, but I stick my new group over there where the I left, I've got a D up here. D is deuterium, remember? How do I show inversion here? One way to show it is dashing my D in this particular perspective. Is that the only way to show inversion? No, you could choose another way, but be careful. You need to show inversion. You can show it different ways. Be careful and make sure you show it the right way. Simple enough. Yeah. Okay, in the next one. Here's my alkyl halide. It's a primary alkyl halide. Here's some stuff. Not sure about it. Here's an aprotic solvent. This is weird. This is divided into two steps. This says first you add this OH thing and that OH thing. This is a phenol, remember? Phenols are more acidic than regular alcohols because phenols have conjugate bases that have lots of resonance. Therefore, phenols' conjugate bases are very stable because they have lots of resonance. Oh, yeah. So the first thing that happens when you put these kids together is an acid-base reaction. Acid-base reaction, hydroxide takes an H from phenol to make this O-, which is called phenoxide. This O-. this O minus is actually my nucleophile. It's an anionic nucleophile because it's an O minus. So this O minus attacks the carbon of my alkyl halide. And if I keep everything in the same sort of orientation, put my D over there to show inversion, I need to put some dashes on that D. Yeah? Yeah. That's Sn2. We're almost done. These are for you. It'll be great. You'll be good at them. One little thing, I don't love how the structure drawing program draws things sometimes. We know sodium don't make bonds, so don't for a second think sodium is making a bond to that sulfur or lithium is making a bond to that oxygen. Metals like that, alkyl halides, no. Alkali metals do not make bonds to things like oxygen and sulfur. Not a thing. Good luck with these. Well, let's do one quick synthesis and wrap up this Sn2 shenanigans. This ether could be synthesized by an Sn2 reaction. This ether, I could imagine that bond being the bond I'm trying to make. And if that bond is the bond I'm trying to make, I can imagine the halogen needs to be on this carbon. And if you go back through all those examples, we haven't exactly said it explicitly, but Sn2 works better with anionic nucleophiles. So instead of just an O that's not got a charge or anything over here so far, I'm going to make this an O minus. I can synthesize this the green route. I could also synthesize this the purple route. Okay, purple means the O is going to be on the six-membered ring thing. Has to mean the halogen is on the other ethyl group thing. Works best with anionic nucleophiles, so there's my O minus. You're going to get to vote. Do you vote for purple? P-R-P-L-E. I promise I used to be good at spelling, and I still am good. I'm just really bad at talking at the same time. Do you vote for purple or green as being the better method? Granted, both of these might be viable, but one is better than the other. Which do you vote is better? Hopefully you know which one is better, but before we wrap this thing up entirely, if you're presenting a synthesis, you often do not want to / are not allowed to start with a charged thing. So you'll need to go back one more step and show me how you make this thing anionic. You'll need to present to me the base that you use to turn that thing anionic. For example, NaH is a fabulous base for deprotonating an alcohol like that. Then you put these kids together and the magic will happen to make your thing. Yeah? All right. Good deal. Sn2. That's a wrap.